Okay, so what we're going to do then is now we are going to make just a couple of optimizations to Bubblesort to show that this really doesn't check. And this runtime over here, this is me after I made the optimizations, right? This was, even with the optimizations, we're going to still see that running with 10,000 items takes 147 seconds. So it still takes a good amount of time. So what are those optimizations we can make? Well, it's fairly simple, right? Suppose we have all these items for, right? We're bubble sorting these items 4, 3, 1, 2, 3, 4, or 5. Well, 5, 4, 3, 2, 1 is our worst case scenario. Well, at the end, when we do our first iteration, 4, 3, 2, 1, 5. Well, that 1, we can kind of lock that into place because we know that once the biggest item just bubbles to the top, right? That's what happens in Bubblesort. The biggest item just bubbles to the top. So then what we can do is that when for our next iteration we can go, oh, so after we get 3, 2, 1, right? We know that during the next iteration, after 4 goes up bubbles up to the top, that should be locked into place, so we shouldn't check any more answers. So we have 4 pairs to check over here. So, right, we only have to really check 4 pairs of items. And over here, we only have to check these items, which is 3 pairs of items. Right? And then over here, we only have to check 2 pairs of items. And over here, we have to check 1 pair of items. And the reason I'm doing this is not because I think Bubblesort's that interesting or anything. The reason is because that this pattern we see, having to check 4 pairs, 3 pairs, 2 pairs, 1 pair, happens again and again and again in in big O analysis. So like say we had 7 items, we'd have to check 6 pairs, right? Then 5 pairs, then 4 pairs, then 3 pairs, then 2 pairs, then 1 pair. Okay, of item. And I'm just doing it like that because it's easier to see. That's if we have 7 items, right? So the optimization we make is fairly straightforward. We just simply take this 1 and subtract runs from it. Now, what does that do? Well, that means that basically rather than checking, right, we used to be going up to the second to last item and checking the item to the right of the second last item, right? So we'd be checking, so we'd go up to 1. So we'd be going up to 2 and checking the item to the right, or rather, we'd be going up to index 3 and checking index 4 against it. Now now for the next round, we're only going to go up to index 2 and check the item to the right of that. Okay, and then we'll subtract that, and we'll only go up to this item and check the item to the right of that. And then finally, we'll just stay here and check the item to the right. So basically, this means that we slowly subtract the amount of work we have to do each run, right? And that you'd think that would move us away from this whole n squared runtime, right? Oh, and this should definitely be a plus. Okay, so we're going to run this, and we're going to see that really doesn't make too much of a difference here. Okay, but right now I'm going to show you why. Okay, so this was if we had 7 items, right? If we had 8 and if I add a 8th item to check, then that means that we have to check 7 pairs, then 6 pairs, then 5 pairs, then 4 pairs, then 3 pairs, then 2 pairs. So, that meant that if we added in... Now, notice that this kind of fulfills what I explained is the definition of an n-squared algorithm. That if you add a nth item, or an nth plus 1 item, that means you've got added, like, not 1 more unit of work, but n more units of work to do. Okay? So, but how does that mathematically work out? How is this an n-squared algorithm? Well, let's go ahead and put this into numbers, right? That was, now we have 8 items, so it was 8 plus 7 units of work, 8 plus 7 pairs, plus 6 pairs, plus plus 3, plus 2, plus 1. But of course, we're working in math, so we'd like to generalize this, right? And rather than doing n minus 1, I'm just going to pretend we're checking n pairs. If you don't like that, just subtract n from our final answer and it'll be perfectly fine, right? Okay, and then I'm going to just reorder this. Okay, nothing scary going on here except for that me just randomly saying, oh, but pretend we have n pairs that we have to check. It just makes the math easier on my end. 1 plus 2 plus, so you're going to have to suffer through it. Plus 3, dot, dot, dot. Okay, and then n minus 1 plus n, right? And that doesn't, and unless you've taken Calc 2, this certainly doesn't look quadratic, does it, right? You don't see an n squared anywhere. But actually, believe it or not, this is equal to an equation. It says, hey, it's equal to this. N squared minus n plus 1. And that is all over and this is all over 2. N squared minus n plus 1 over 2. Don't believe me? Let's go ahead and check Wikipedia. Watch this. This is actually really a common one. 1 plus 2 plus 3, dot, dot, dot. Let's see. Nope. Oh, plus n. Oh, there it is. N. 1 plus 2 plus 3 plus 4. Let's go ahead and check the sequence over here. Oh. Apparently I messed up there. It's not minus, it's times. It was just, there was a blotch. I thought that was, I'm reading my notes. Okay. But the summation of these items is, right, the sum of 1 to n added together is n times n plus 1 over 2. And this is something you learn in Calculus 2. Right? No, it's not that. Sorry. N times n minus 1. Now I know where. N times n plus 1 minus 2. There we go. So now what we do is we can multiply this out, and that's equal to n. That's the issue when you go off of memory. So n squared minus n squared plus n, and then that's divided by 2, and that's divided by 2. Right, and just like we saw in the original algorithm, in my original analysis, right, as n gets to a monstrous size, the n squared becomes not just monstrous, but utterly monstrous, while this just stays merely monstrous and not actually nearly as intimidating, right? And that was indeed like half the length of time, because we were doing half the work, right? But we were still adding in a whole lot of... Even though we were just having the amount of work essentially we had to do if we were comparing all pairs, watch this, if we were comparing all pairs, it would look something like this amount of work to do. And essentially all I did was just simply cleverly half the amount of work I had to do. And that, in the end, did not make much of a difference at all.